Good afternoon, everyone. I'm very pleased to welcome here in Paris for this fourth version of the Electrochemistry in Nanoscience meeting, which is a joint meeting with the Echems conference. So on behalf of the Electrochemistry group of the French Chemical Society and on behalf of the scientific board of the Echems conference, we are very pleased to have you here in the University Paris Diderot, University Paris Diderot, with Professor Jean-Christophe Lacroix and his team. You are very pleased to be the host of your organization here. So, very few words about this meeting and some practical information that will be given to you in order to make your stay as smooth as possible with us here in Paris. So this conference is aimed and it's focused on the electrochemistry in nanostructuration of substrates and energy. And the major goal here is to show contributions of electrochemistry in nanostructuration of substrates with a special emphasis into molecular electrochemistry for photovoltaic, artificial photosynthesis, and CO2 reduction valorization. We have 6 keynotes or invited conferences that are listed here from Professor George Whitesides, Professor Gretzel, Professor Seidels, Doronzier, Palassin, and Crooks. And all these conferences will be given from this afternoon until Thursday afternoon. We have in total 40 oral communications and 55 posters, and we have 140 participants from 23 countries from over the world. And of course, you will see 3 exhibitors of scientific equipment: Biologic, Ametec, and Origalis. And these are the contributors and the sponsors for the financial support that we needed to have in order to organize this conference. And now I will let Jean-Christophe Lacroix give you some indication about the practical aspects of the meeting here.
Well, thank you, Fethi. So I'm going to focus on the practical and local organization. So we are located right now here in this building, the Buffon building. The Buffon building is the biochemistry building of the university. In front of it, you have the physics building, and we will have lunch just nearby, 1 block away from here at this location. And you have a small park here after lunch to be in the sun if you wish. The poster session will be held in the chemistry building, which is located over there. So it's a straight line between here and the chemistry building over there. And the posters will be on Wednesday. They will start to be held Wednesday morning at 10 o'clock, and we will have 2 poster sessions. All poster will be shown at the same during those 2 days, Wednesday and Thursday. The other thing that has to be so a couple of social events during this meeting. The first one will be tomorrow night. So you all received a ticket that is a cruise on the river, the Bateau Mouche, and we are supposed to leave the meeting tomorrow after the session. We will all go at this place, so this is an easy trip in metro. We have to go to the Bibliothèque François Mitterrand station, and we take the subway, the RERC. It's straight to this station, Pont de l'Alma, and a small walk to this location, and then we will take the boat and cruise on the river by night. In fact, the ticket is valid for 1 year, so if you don't want to go tomorrow night, you can go during the weekend, or you can even come back to Paris and go with your wife in any kind of at any convenience for you. The second social event that we'll have is a banquet. The banquet will still be on the river, but the boat will be fixed and will not cruise. We will have a very nice sunset on the highland of the river and the Notre Dame church. And in the program, we forgot to put the exact address. And the exact address is Café Barge 5, and this is the telephone number in case somebody get lost. Okay, so maybe you can write it up and ask later on. So in fact, we are located here, and we will have a short 15 minutes walk to go from this from the conference room here to the banquet that is on the other side of the river. The last thing, you all received this kind of object, the Elecnano multifunctional devices. As you see here, we have a laser pointer on that side, a pen on the other side, and it's not obvious, but you have also a USB key in the middle. So we thought that it will be a nice souvenir for everybody. And then, on behalf of all the persons that got into the organization, and particularly Sophie Griveaux, Jalal Gilans, Steve Reisberg, Pascal Martin, and Hyacinthe Randriama-Azaka, and all the persons that really helped to set up this meeting. We are pleased to welcome the first plenary lecturers that will be introduced by Alexander Kuhn. Thank you very much, and enjoy your stay in Paris.
Good afternoon, ladies and gentlemen. So my name is Alexander Kuhn from the University of Bordeaux, and it's my great pleasure to be the chairman of this first session of this meeting. And it's an even bigger pleasure to introduce, and it's also an honor to introduce our first plenary speaker of this afternoon. And as Fiti Bidieu already mentioned, we have the honor to have with us this afternoon George Whitesides from Harvard University. And he will give us a very nice and interesting lecture, which was a little bit secret in the beginning because we had a really hard time to get a title from him. So we discovered only in the last, let's say, few minutes or few hours what he's going to present to us today. Before he is going to start, I would like to say a few words about his career. Actually, George Whitesides is somebody who you don't really have to introduce because he's so famous and so well known that in principle everybody should know what he's doing and what he has done in the past and maybe also a little bit what he's going to do in the future. But maybe for the younger participants like the PhD students, just a few words to describe a little bit his career. So George Whitesides was born in 1939 in Louisville. And then he went to Harvard for his first degree in 1960. Afterwards, he moved to Caltech in Pasadena, where he got his PhD in 1964. And then, and this is something I didn't really understand in his curriculum, he got his PhD in 64, but he was already a faculty member of MIT in 63. So maybe there is some secret that he didn't really explain to us. After a few years at MIT until 82. He joined the chemistry department of Harvard University in 82, and he was there the department chairman from 86 to 89, and he's still now working at Harvard University and has a very large group there. He has extremely high number of awards. I counted them just a few minutes ago, and it's something like 50 very prestigious awards, so I will not go through all these awards and tell them to you, but maybe I will start just with the very first award, and I will tell you then the last award that he got, the latest award. So the very first award he got in 1968, which was an Alfred Sloan Fellowship, and then there are 50 other awards that I will skip, and the latest award was the Gold Medal of the Chemical Heritage Foundation in 2010. He is a member of many different societies, and he has honorary PhDs from different universities. And I could spend 1 hour of presenting all the different activities that he has and he's had, but I think this is not so interesting, and it's much more exciting to listen to his science talk. So it's my great pleasure to welcome Professor Whitesides as the first plenary lecturer of our meeting. And so please, George, should tell us something about the opportunities in commodity infrastructure for nanomaterials and electro. Thank you very much for coming.
Thank you. So it's a pleasure to be here, and the reason that I didn't tell you my talk title until recently was that I didn't know my talk title until recently. What it's going to be on is an overview of what I take to be opportunities in this intersection between production of what I call commodities, that is water, power, food. I'm going to concentrate here on energy, power, but that's intimately connected to water, and we won't talk about food. But a reason for doing this is a philosophical issue that comes up periodically in science, and I think is very important in electrochemistry now. And that is, does the best science come from starting with the science and working forward to more science, or does the best science come from starting with problems and working backwards to the science necessary to solve them? I think electrochemistry right now is in probably the best situation it's been in the time I've been doing science, because there's so many interesting things to do. But given that fact, it's important to have a sense for what the problems are. So this is an overview talk. I'm going to focus mostly on what problems are, and then we will, to some extent, talk about how those connect to electrochemistry and nanochemistry. The first thing I want to raise with you is an issue which I think chemistry generally has to deal with. And that is, should we be thinking about the research that we do in terms of, first, the function or problem that it solves, or in terms of the science or understanding from which it comes? And there are different points of view about that. And of course, the answer to that question changes from time to time. The field where this is probably most obvious right now is organic synthesis, which has been a field of science and has now become a field that solves problems for the pharmaceutical industry and things of that sort. So it's a very important and interesting field, but it's become a technical field. So it's important to know what problems that you're going to solve there. So I'm going to give this talk in terms primarily of function and in terms of solving problems rather than in terms of basic understanding. But basic understanding underlies everything that we talk about, of course. And then a second issue is that in this spectrum of applied science, basic science, or that should be fundamental research, where do we stand? And I think this is an area that's very much at the level of basic. That is, it is understanding, but understanding with an idea to solving problems, as opposed to understanding with no idea as to what one is doing. And then finally, there's an issue which I think faces the academic community generally, which is that is our purpose in life to write papers or to solve problems for society? And I would argue strongly that it's actually to solve problems for society and not to write papers. And one nice thing about getting older is that you actually don't care very much about writing papers anymore, so that solving problems is much more interesting. Now let me show you the entire story in one slide. This is from a Department of Energy website, and it is a flow chart showing inputs to the energy sector and outputs. And this is something which you can download for yourself from the DOE, and you should post it in your bathroom when you get up in the morning to brush your teeth. There's a mirror. If you look in the mirror and see where you put your face, you see your face, and then put this where you would see your face, you'll learn a lot, because it's more interesting than your face is. So there are a couple of things here that are important to notice. Now return to these. In output, more than half of the output that goes into the system is lost. So about 55% disappears somewhere along the way. In terms of input, petroleum, natural gas, coal represent about 85%. The thickness of this line is the thickness, the amount of energy produced in that form. So if you have 85% roughly of the world's energy being produced by combustion, that's not going to change very rapidly. Maybe over 100 years it'll change, but it will be very slow, simply because of the capital cost to do that. Nuclear is the only other significant, nuclear, a little bit of hydro, are the only other significant sources. And nuclear has gone through the series of interesting problems. France is one of the leaders in nuclear energy, but it's going to be increasingly difficult for the world to accept nuclear plants after Fukushima, because there's this real concern that the plants are under-engineered. Then issues like solar and wind and geothermal and biomass are really quite small. And one of the interesting issues to ask here is if you look at the amount of research that goes into nuclear, coal, natural gas, and petroleum relative to the amount that goes into solar, you ask the question of whether the resource allocation is correct. Because there is a hope that solar might get to be as much as 10% of grid at full maturity, but it's not clear that it will make that or not. So that's the first general part of the problem. Now, this is a conference that deals with nanoscience and nanotechnology as well as electrochemistry, and I'm going to make this a prominent part of the talk. Let me explain a little bit about what nanoscience is perceived to be in the United States by starting with what it is not. And what it is not is a quantum change in science like quantum mechanics or polymers or genetics and genomics or the World Wide Web. It's not a single thing that has dramatically changed the world. What it is seen to be now an integrating subject. It's a field of science that is at the interface between things that are big and made top-down and things that are small, mostly made by molecular means. It integrates a wide variety of topics. So it's a very important area, but it's quite different in its character from the revolutionary topics here. It's an evolutionary topic rather than revolutionary. So here's what I'm going to talk about. A little bit of an introduction, some discussion of a very important point that is pretty commonly neglected in these discussions, which is when one is talking about energy, should one talk about it from the point of view of the supply side, that is generating energy, or should you talk about it from the demand side, which is consuming energy? And I will argue with you as a group that there are probably more opportunities for new science in conservation than there are in production, but I could be wrong in that. I'm going to talk a bit about some of the major energy production technologies, combustion, nuclear, biomass, solar, wind, and talk about what the contributions are that some combination of nano and electrochemistry can make to these, and then close with a few remarks at the end about areas that I think are particularly promising. So, let's start with a fundamental reason why we're doing this. There's an old equation which says that well-being is approximately given by the ratio of energy to people. So the more, you can also do this if you're a chemist, it's the ratio of sulfuric acid to people. And sulfuric acid is a general measure of industrial activity, as is energy production or consumption, a measure of the if you like, the affluence of the society. It's a very interesting equation because it says that if you want to improve well-being, there are two ways of doing it. You can generate more energy or use less per function, or you can have fewer people. And the fewer people part of it is something which is actually pretty troublesome because there is in that very simple an equation a suggestion of very large-scale social disruption if we don't deal with some of these problems. So this is not a curiosity. This is really very important. And what are the constraints that we face? And you know these, but it's good to put them out at the beginning. Energy we actually don't have an energy problem for a few hundred years if we can continue to burn fossil fuel. But we may not be able to. That's still, in my view, a little bit unclear, but I think we should be conservative in that. So climate change, or as the people who do this now say, climate variability, may limit our ability to continue to generate energy by combustion of fossil fuel. And what the variability really means is that the prediction is that it's pretty hard to know whether the temperature goes up or down. It probably goes up. But what one expects to see is many more anomalous events, things that unexpectedly cold winters, unexpectedly warm winters, massive storms, things of this sort. Those are problematic. So that's the issue here. Energy and water, it's important to remember that really the big problem for the next 50 years is not probably energy, but it's water. Beijing is about out of water, and that's in the order of 20 million people. Mexico City is 15 million people, and that's out of water. And the Chinese are going to solve the problem by pumping, whichever it is, the Yangtze north, using an enormous amount of energy to do that. The Mexicans have no idea how they're going to deal with the problem of Mexico City because it's about to become uninhabitable. And the problem is that it's in the middle of the country and it's uphill, so you can't pump water to it. So it represents a really major issue. So the point here is that when you talk about water as the limiting factor and probably a major source of conflict, in order to solve the problem of water, you have to have energy, which gets us back to this problem. And then finally, in energy and nuclear, the real problem here is not accidents like Fukushima, but weapons proliferation a la Pakistan. So the issue is that as the technology for making nuclear power generation widespread, then the technology for making nuclear weapons becomes widespread, and the world is not a stable place right now. So these are important and complicating problems. Now, a couple of things to remind you of just as kinds of background. The first is really this. We don't think of a joule as a lot of energy, but a joule is a volt coulomb, and that's about 10 to the 18th electrons. That's a lot of electrons. So when you think of events in terms of one electron doing something, as a photon coming into a photocell and producing an electron, that's a lot of them. So we have to think about that. The second thing is that the world usage of energy right now is about 14 terawatts. You can go back, a watt is a joule per second. The United States is about a little over 3 terawatts. Europe is about the same number. An enterprise like this, the standard package for producing power in the world is always 1 to 2 gigawatts. So coal plants are a gigawatt, nuclear plants are 1 to 2 gigawatts. And if you look at that and realize how many of those have to be constructed in order to make these kinds of numbers, it's really pretty disconcerting. And then China right now is bringing on board a 1 gigawatt coal burning plant per week, roughly. And if you're going to make some headway in producing that amount of power by replacing combustion, you need to build approximately a nuclear plant per week for the next 30 years or something of that kind. And that's clearly impossible. So no matter what you intend to do, you simply can't change this kind of usage in a very straightforward way. Now, if you look at population projections, 14 terawatts now, 30 terawatts in 2050. This is the short-term problem. A major part of this 30 will go into improving standard of living of the poor, who are going to insist on it, particularly China and India. And water is an issue which will be a significant consuming part of this 30 watts. An important part is this, and that is that what the world cares about is what the function is that's being served and how much it costs to serve the function. They actually don't care about electricity or things of that sort. So when you're thinking about it, think about how you solve the problem, which is to provide a function, indoor lighting, for example, not how to make the most energy. In the United States now, we're about to outlaw incandescent light bulbs. So all the lighting in the U.S. will have to be solid state in the future. And those are interesting kinds of changes. These issues we've, in a sense, sort of talked about, but this is an important one here to pay attention to. All solutions for these very large-scale energy problems require lots and lots of capital. And capital is expensive, and the world is capitalist, even France, the United States certainly. And so there are no solutions if you don't have the money to build the plants. And the money to build the plants right now depends upon the economy, and there isn't very much money in the economy for a variety of reasons. So there's a complex of factors there that makes things often complicated. And finally, this point down here, the developed countries and the developing economies are often, maybe usually, in conflict over these issues. And the trouble is that the world population now is 7 trillion going on from some number like that, 7 trillion. And it'll probably double in the next 50 years or so. So there are a lot of people in the developing economies who are very unhappy with the current situation, or would be if they knew something about it. So this conflict is a potentially problematic one. Now, if you look at what we all do as research, the issue here in this kind of discussion says that what can be done will be determined on a risk and time discounted cash flow model. This is the standard capitalist model for doing things. And for those of you who are students, this is the one thing you must know about the world. You don't necessarily know how to model the Stern layer or something of that sort, but you have to know how this works. And the notion here is that if you look at cash flow, cash coming in, cash going out, as a function of time, the way this works is that you say you're doing research, so you're somewhere here. And to do research, somebody has to pay for it, so you have to borrow money. And you borrow the money, and you also have to pay interest on it. So the total outward cash flow from a research project goes like this. And then at some point, there's a benefit that society recognizes, and there's profit, we call it here, something coming in, a benefit. And at some point, you hope that the integrated area of this cancels this, and the net cash flow turns positive. But the point of interest here is that in the current capitalist model, the longer you're paying interest, the less interesting the prospect is. So early research is always unattractive. Further, if the technology that you're trying to invent is uncertain, it's risky, that's unattractive because you have to discount its value for risk. And what this says now is something that's pretty widely accepted, which is that large corporations will no longer invest money in long-term research. It just won't be done. So it has to be done, any research that's done will be done in universities, but you have to ask why people will pay for it. And electrochemistry and energy is a perfect combination. This is an area that will get a lot of money if you make the case clearly. Here's a second curve, which is a very useful one, and it has to do with all technologies, including, in this case, nanotechnology. This is, again, curve of time, and here is a curve of expectations on this axis. And what happens, and you've seen it very clearly in nanotechnology, is that there was wild hyperbole at the beginning, claims of robots climbing out of test tubes and eating the world and free energy and things of that kind, followed by grave disappointment. It's a little bit like marriage in a certain sense. And then this is followed by this stable growth in understanding what's really going on. And nanotechnology is in this area now. It's over this stuff and it's moving forward. But what it has to do now is to prove its worth. Electrochemistry has proved its worth. Nanotechnology has done it, but only in the area of microelectronics. So now we're going to go into another part of the talk, and the only thing that I want to say here is that everything I'm going to tell you is opinion or prejudice. So probably if you're students, the wise thing to do is not to believe a single word of it, and that makes your life easier. So let's look at trade-offs. Here are the options, and I told you this. Burning something, hydrocarbons, gas, coal,
generating using basically thermal cycles in a nuclear process. Hydroelectric, biomass, and geothermal are blocked together, and then wind and solar are basically both ways of coupling solar energy. This one through wind is produced through heating of the ground and then activity that follows from convective movement of the air. So what are the things that happen here? We've talked about climate change, and then there is a chemistry associated with all of these gases that's extremely interesting. You may or may not have followed it, but when hydrocarbon fuels, crude, became scarce 10 years ago, what happened, and happened all the time in the capitalist world, is that people went out and looked for new sources of hydrocarbon. And what they found was, in fact, natural gas. And so right now the world looks like it's awash in natural gas. There's so much natural gas coming online that it's just almost unbelievable. The United States is maybe an energy exporter in the immediate future. But what that has done is it's lowered the cost of energy of many sorts to the point where wind and solar are presently pretty unattractive. And so the availability of natural gas has done a major job in reducing the investment in wind and solar. And you'll see those kinds of things playing out over the next period of time. Hydroelectric, there's really not very much we can do about hydroelectric. That's saturated. Biomass, it's not really clear how important biomass is going to be generally. It'll certainly be important in Africa and in Brazil, but otherwise there are two problems. One is competition with food, and a second is a more subtle technical problem, and that is that when you're growing something on the ground, you grow it in a flat area, and then you have to collect it in order to put it in the reactor that you're going to do whatever you do with it. And there's a surface to volume problem there. And what it does is that it makes it complicated to take results that come from small test demonstrations and scale them to world-scale plants. You just can't go from something that requires collecting over a large area and bringing it to a central point for the reason that the collection costs get to be very large. So my guess is that biomass is going to be pretty limited. Geothermal is already finished. It's pretty much saturated, barring the fact that we convert Iceland into an energy factory. And then the problems with wind and solar are just that sunlight is very dilute, and it's hard to get something from it. Hydrogen is, again, something which is vitally important to the electrochemical community, but the problems here are, first, where do you get it? And second, of course, it's not a source of anything. It's a way of storing energy, and very important from that point of view. So if you start by this diagram and you ask where is the real opportunity, I start by saying if more than 50% of the energy that's produced here is lost in transmission or in some other point, that's a great place to start. And all of these areas, tribology, corrosion, and wear, all have big electrochemical components, but are not popular, at least in the United States, in electrochemistry. Thinking about materials to move electrons around more efficiently, and then issues of this sort, like building solid-state devices. A solid-state light is about 99% efficient. These lights in here, the incandescent lights, are about 1% efficient. So that is solid-state electrochemistry or solid-state electrochemical physics, and very interesting as an opportunity. In the area of carbon-containing fuels, there are a whole series of materials issues, which I think you're probably pretty familiar with. Carbon dioxide management, we don't know how to do it. Catalysis is everywhere. High-temperature materials, separations, machinery, I'm going to talk about some of these. And the point that I would make to those of you who are students is look at that list and ask how you can couple the thing that you know how to do, which is electrochemistry, to each of these problems. So we'll talk a bit about how you couple electrochemistry to CO2 management, but how do you make catalysts? How do you think about electrons and ions moving around in high-temperature materials? Can you use electricity to enable these kinds of separations? And then what do you do with electrochemistry to deal with these sorts of problems? And you say, are separations, just to take that as an example, are they a problem? Is this really interesting? And the answer is that if any of you would like to retire forever, all you have to do is produce a good membrane that will separate methane from N2 and CO2. And the reason for that is the Middle East has a staggering amount of natural gas. But the natural gas is about 40% natural gas, and the rest is nitrogen and carbon dioxide. And so the principal problem in unleashing that source is separations to make the material available. Now, there's some very interesting trade-offs here, and this is both something which is interesting from the point of electrochemistry because electrochemistry goes a different way and also offers opportunities. Let's just think about the efficiency of burning something. So you have a hydrocarbon and oxygen, you burn it to CO2 and water. You go to higher temperature and you get higher Carnot efficiency. And this is the reason for the efficiency of diesel engines. You basically cannot beat a high temperature direct injection diesel in terms of the thermodynamic efficiency with which it produces power. It's about 75% at optimum. And that's much higher than you can do in anything else, including right now electrochemical systems. So you've got higher Carnot efficiency. It's very hard on materials because you're operating close to the melting point of some materials, basins for diesels, but because you're at temperatures now that are high enough to cause the direct reaction of oxygen and nitrogen. What happens under these circumstances is you get NOx coming out if there's any excess oxygen. If there's any excess oxygen, you get NOx. If there's any deficiency in oxygen, you get carbon. And so operating the systems become a real problem. So NOx, it's commonly produced, N2 plus O2 to give NOx. It's a pollutant, but it's also a major greenhouse gas. And so as you go to higher temperature to get higher Carnot efficiency, you also require more after treatment, which lowers the efficiency and raises the cost. And trading all of that off is something that requires a lot of careful thought. And so when you're students and you're doing something, remember that in this area, perhaps more than any other that I know, everything is a question of trade-offs. You can't just work on one part of the problem. Carbon management, this is a wonderful area because we have so little understanding of how to do this. Everyone agrees that CO2 we're going to have to do something with it. And there are various schemes for doing it. The only point that I would make to you here is that if you look at what everyone is relying on, that is sequestration, meaning you take it, you pump it down hole, you forget about it. We have no idea whether that's going to work, and there is no demonstration that it works. I mean, we do not at this point know whether you can sequester CO2. The problem, among the problems, is one of them is that you put CO2 down hole. If there's 1% leakage from the CO2 you put down hole, and we do this for 100 years, and that's the time scale you have to think about, then 100 years from now, we find that we are producing as much CO2 by leakage as we're producing now by burning something, but we have no way of turning it off. And, by the way, we don't know how CO2 reacts with the minerals downhole. We don't have any idea how to convert it to something else. It's a really major problem. And there's some quite clever solutions being proposed, but it is really not one that we understand very well. So, CO2 utilization. If you assume that you're working with an oxygen-fired coal plant, and what comes out of it is relatively clean, hot CO2 and not much of anything else. So you've got an ideal situation. You've got hot CO2 uncontaminated by nitrogen. What do you do? So right now, if you take this and you compress it to the pressures that would be required for pumping downhole, but you don't move it anywhere, you will have used somewhere around 50% of the energy that you generated to do that. So that halves the efficiency of your power generation by a factor of 2. And people don't really know what to do about these issues of geochemistry and the long-term sequestration. So the two interesting problems right now is what can you do with photosynthesis and what can you do with other sources of chemistry or other kinds of chemistry. And there's an interesting idea which is beginning to crop up. Photosynthesis has the problem that photosynthetic energy is basically very dilute relative to the scales required for energy generation. That means CO2 consumption. So people are beginning to think about other ways of concentrating the energy, and one of the interesting ones is that to ask the question, could you do photosynthesis without using light, that is supplying the energy, let's say electrochemically? And there are some schemes being developed for that. None of them are practical at this point, but I think it's an imaginative idea with unknown consequences for the overall cost structure. Nuclear, the problems here are not primarily nano, but probably the most serious problem is this regulatory approval issue, which is based on public perception. Regulatory approval just takes forever. It can take 20 years to approve a single plant, and if nuclear is going to make a big impression, we have to build a plant a week. Proliferation, we've talked about waste and decommissioning, high impact accidents, and then this issue is quite an interesting one. In order to deal with proliferation, there is an argument for going to an alternative source of fuel. That is, instead of using uranium, you use thorium, because you can build a good fuel cycle on thorium. The nice thing about thorium is you don't make as much plutonium, which means there's less probability of proliferation, but thorium isn't very concentrated anywhere. So you have to think about the environmental and energy costs of mining the thorium. The energy costs are tolerable, but the environmental costs may not be. So is there a way in which one can contribute to that set of problems, particularly waste and decommissioning by electrochemistry? And I suspect the answer is yes. Now, photosynthesis is something which energy people very commonly refer to, either directly or indirectly. I just want to review for you very briefly how photosynthesis works. You have sunlight. It goes into the leaf. It is absorbed in structures in these thylakoids that are in the leaf. And then what's interesting here is that the sunlight does not itself fix the carbon dioxide. What sunlight does is to drive a system here which generates oxygen and basically, and I'll show you how in a moment, generates ATP and NADPH, which are then used chemically to drive, as reagents to drive another cycle, reducing agent, to take carbon dioxide in a number of steps and convert glucose. But the point of interest is that there's a clear division here. It's chemistry that's used to fix carbon dioxide, and mostly just straightforward enolates and reductions. And then the sunlight drives this photosynthetic process, which basically makes an ion gradient across a membrane. So the question is, could you drive this rather than with NADPH generated photochemically? Could you drive it with NADPH generated using some other chemical process? And then if you look at the actual processes that go on down here, they're purely electrochemical. Basically, the sunlight comes in. There's a very complicated series of processes in which energy is transferred from a series of centers in proteins embedded in a membrane, with the overall effect that what one does is to take protons and pump them across the membrane to make a difference in proton concentration across the membrane, and then that is released in a piece of machinery that makes ATP from ADP. And up here somewhere you make an ADPH, and down here you make ATP, and then they go to the Calvin cycle. But every part of that is electrochemistry. And these issues of harvesting energy across membranes, proton here or sodium, potassium, is a purely electrochemical problem. It's amazing that although this is the most widely used source of energy on the planet, there is no laboratory demonstration of this kind of chemistry. Not a single one as far as I can see. And that means it's a wonderful opportunity. Biomass. There are a series of issues here, and probably this is an important issue for nano, but not so much for electrochemistry. So one of the issues here, just to mention, is that when you make biomass, are you going to burn it or are you going to do something else with it? And there's a strong argument that what one really wants to do with biomass is simply to put it in the current reactors that are used to make gasoline because they don't care what you're putting into them, and go directly to shift gas and then go from there. But it may well be there are fermentations that make sense for ethanol or butanol. Biodiesel is an interesting case. The best source of fuel for biodiesel is soybeans. And the reason for soybeans is that soybeans make protein and soybean oil. And you collect the soybeans because you're feeding them to cattle. And the cattle don't like the oil. So that if you take the beans, which are already collected, squeeze out the oil, basically the protein value of the meal goes up, the cows are happier, and you have the oil for free. That turns out to make economic sense. But most of the schemes right now for making biodiesel don't make sense. So there's an interesting problem there. Here's a wonderful electrochemical problem. In order to grow something, you're going to probably have to add fertilizer. And fertilizer will require fixed nitrogen. And right now we make nitrogen ammonia by taking nitrogen and hydrogen in the Haber process, making ammonia, reducing it as far as it can go. Then you take that and you burn it to make nitric acid to go as high up as you can go, and then you combine the two. That can't be the right way of doing things. I mean, it just makes no sense to make nitric acid by burning ammonia. So why can't you go directly from N2 plus H2 plus O2 to ammonium nitrate? And the answer is we don't know how to do it. Other issues which we won't talk about here but are relevant in other parts of the problem. Photovoltaics. Enormous enthusiasm for photovoltaics, and in many parts of the world absolutely justified. There are a number of ways of using solar energy. This is one. You can do inorganic or organics, perhaps. Solar water splitting, which is simply a coupling of this. Well, it's not simply, but it is a coupling of the energy separation generated in photovoltaics into something that does chemistry directly, and it's important for reasons we'll talk about. Solar thermal, high temperature, I happen to think this is very interesting, the artificial photosynthesis. So there are a wide variety of ways of thinking about this problem. But take just a brief look at this table, because it's one of the ones that is used and abused to justify this area. If you look at the top line of this, solar power incident on Earth in all directions, it's enormous. Solar power average in the United States, just falling on the U.S., it's also enormous. U.S. electrical power consumption, 10 to the 12th, compare this number with that kind of number, and everything looks terrific. When you get down to more local things, solar power on the roof of a house, 10 to the 4th watts, and then mean solar power per meter squared on the U.S. surface is about 100 watts. And right now, solar cells are probably about 10% efficient, so practically you can harvest in the order of 10. That'll go up as evolution goes on. But there's just a very straightforward thing, which is energy available in sunlight is pretty dilute, which means if you're going to generate a lot of energy, you have to have it spread out over a lot of things. It's a very strong argument for conservation and for function. And an example is that if I take this much space, this much solar panel, and I use this in Europe or the United States, it doesn't accomplish very much. If I take that much solar power and panel and use it to power a light bulb, not a light bulb, but a solid state light in Africa, it provides more than enough light that children can read at night and change the structure of the society through education. So the value of power depends entirely on the function that's being served and where it is. So there's no question that solar will be important in various ways. The question of whether it will make a major contribution to power consumption in the U.S. and Europe, I think, is not clear at the moment. So you all are probably more than familiar with this kind of thing. The point that I would make here is simply that what you're doing, it's probably easier to see on this slide. What you're doing is basically you have the problem of separating charge. The light comes in, you generate a hole in an electron, and you have to arrange the band structure in such a fashion that it is thermodynamically feasible for this electron promoted from here to here, falling to there, to go through an external circuit and come back to get to here and do work in that process. And the scales that are required for that to happen, that is for the electron and the hole, to get to the collection electrodes rather than combining just to generate heat, are 100 nanometer scales. So this is a nanometer, it's a nanotechnology problem very generally, and also an electrochemical problem because you're moving charge around. And some of the very interesting work that's been done in this is purely solid state silicon, and then of course Michael Gretzel's very interesting work in dye-sensitized systems has used more diverse methods of doing charge separation. But the basic problem is the same. Now, here is where economics comes in. These are a series of efficiencies ranging from triple junction cells that are, some of them are actually up around 60%, the ones that are space qualified. The point, though, to make in this is that there are only two right now that are used in any substantial amount. One of them is silicon, and the other is the First Solar cadmium telluride cells. And the only ones that actually seem to work reasonably well economically without a subsidy are the First Solar cells, the cadmium telluride cells, which are not, enormously efficient. So how is it that you would install large amounts of this when you get so much better efficiency here? And the answer is simply cost. I mean, that's all there is to it. Now, I can't imagine that the cad telluride will be a long-term solution. There isn't enough tellurium, and cadmium is very toxic. So it has to be something else. People are working hard on copper selenide-based systems, copper sulfide-based systems, and there will be alternatives here. Dye-sensitized cells is another possibility, or we may find better ways of working with silicon and gallium arsenide. But the issues at the end of the day here are purely economic. To think about this problem as a scientific problem is not probably a sensible way of doing it. But of course, when you're working with solar or wind or other things, there is a second problem, which is a critically important one, which is purely electrochemical in many options, and that is energy storage. Because when the sun goes down, that's when you actually need power. So how do you do it? Here are the contenders, the major contenders here. Pumped water, that is, you just take the electricity. When you've got it, use it to pump water uphill, and then when you need the power, you run it back down a hill. The overall efficiency, round-trip efficiency, is about 50%. And the problem with that is you have to have a hill to pump it up because you can't build towers. Compressed air is an alternative to that, which is actually fairly interesting. Thermal energy is not very attractive for a bunch of reasons. Batteries, purely electrochemical. We desperately need new batteries and capacitors. People are trying flywheels, storing energy in the kinetic energy of rotation of the flywheel. And it works, but it's probably not a good method of doing large scale. Redox fuel cells is something you as a community could do a lot with, and redox batteries. So a redox battery, this is an area that's getting a lot of attention. You just have a tank, and when you have electrical energy, you pump let's say an oxidizable material past it, you separate energy that way, and then you run it backwards. And the round-trip efficiencies there can be in the order of 75–80%. So that's not bad. Wind, probably not much of a problem for this community. And fuel cells are enormously interesting and have proved very difficult. Let me show you what some of the problems are here. Fuel cells have the feature that they bypass the thermodynamic limitations of Carnot and are very attractive from that point of view. They're very materials intensive, so that one needs to find ways of doing them with cheaper materials. The fuel, the only one that really works well right now is hydrogen. And people have done some work with methanol, but it's a little bit complicated. A very attractive option are these solid oxide fuel cells, where you can put anything in from peanut butter to hydrogen, but they're tricky to run, and they operate about 1,000 degrees. So what we need here, among other things, is ways of doing this more efficiently and ways of getting better catalysts, since every one of these is a catalyst problem. So you know the basic ideas here. The point to represent here as a key problem is this one. That is that a problem which electrochemistry is probably uniquely qualified to deal with is that in making a fuel cell run, you're going to have oxygen and hydrogen. The efficiency of that is limited right now by the efficiency with which, thermodynamic efficiency, with which you can reduce oxygen to water. And if you're going to generate hydrogen, then the thermodynamic efficiency of that is limited by the efficiency with which you can do electrolysis. Both of those are in the order of 50 or 60%. So the overall round-trip efficiency there is in the order of 40%. And that's probably not acceptable. So we need better ways of doing both of those and need better ways of getting around platinum, which is the key catalyst, because it's too expensive and too scarce. Only electrochemistry can do that, and catalysis. So if you look at this problem, the key thing here is the catalyst particle, and over here we can do better, but it's really that problem that limits the capability, that and then the electrochemical losses and diffusion through there. So if you look at the oxygen electrode, which is to me one of the most important problems to be solved in the energy area, what you find is, if you look at activity as a function of the potential, that you get the best activities out of platinum and platinum alloys and palladium and rutheniums up here somewhere. How do we do better? And there's a lot of effort now, mostly focused around various catalysts based on cobalt. And it is promising, but it hasn't yet gotten to things that really work. The special problem of hydrogen is that there are lots of ways of making it. We've got problems with storing it, but basically it's been promoted primarily in the United States incorrectly as a source of energy. And so people say the hydrogen economy and this and that. It's a storage system, it's not a source of energy, because you have to do something to make it. Either you have to have natural gas and shift it, or you have to electrolyze water, or perhaps you can find a direct solar method in the future. There are lots of interesting possibilities. But we can't presently generate it in a way that makes sense for a large-scale economic use. And then storage, we don't know how to do that either. And so lots of problems there which are going to have a big component. Conservation, I think all of these are pretty clear. But let me point out that there are a couple of these. Corrosion. Corrosion in the United States represents a loss of somewhere around 10% of the gross national product per year. Stuff just dissolves. Electrochemistry. Reduction of friction and wear, there are big electrochemical problems in both of those. If you can make contributions to these, it may well turn out to be more important than generating energy in the first place. And so if you look at these things, this is an enormously practical and interesting problem. Finding out how to get around this issue of balancing the oxygen-hydrocarbon ratio in a diesel engine in such a fashion that you don't get NOx and you don't get carbon black. These are problems that are probably more important than most of the energy generation problems for academic laboratories. And then this is an example of an interesting failure. This is a high-definition plasma TV screen into which went many hundreds of millions of dollars of development. And they'll probably never be used because that probably consumes about 1 kilowatt of power. And these are hot enough that if you put them in your wall, the wall will catch on fire. So they're a hazard of that sort. So here's an example where we're already seeing technology beginning to be discriminated against on the basis of energy efficiency. This will be used, that will be changed, that apparently is going to be discarded. All right, now let me begin to finish this off. What are the strategies that, at least in the U.S., and I suspect it's probably France as well, people who are scientists in materials or electrochemistry or nano are using to try to involve themselves in the area of energy? And the first one, the one that's probably most common, is to do whatever you were doing anyway, and you call it nano or you call it energy, and you try to get money for it. I mean, you actually don't care, but it's as we say in the U.S., rebranding. And that's actually worked pretty well for a while, but it's beginning to fail now. There's a second approach, which is to join an ideological crusade. And in the U.S., the ideological crusade is for solar because it's regarded as clean and attractive. And I'm all for solar, but the problem with solar is that it's not clear how large a contribution it can be relative to dealing with some of the problems with combustion, say. And so that's a good thing to do because it works in the peer review system, but it has its problems. You can actually try to solve problems, and people are increasingly beginning to do that, and for those of you who are young, I would recommend it. And there's a problem that I'm not going to talk about here, which is the technology transfer problem. If you have an idea in a university, how do you actually make it into reality? That's a different set of skills, but really, really important. Because if you're trying to contribute here and you don't focus on technology transfer, it unfortunately doesn't end up making very much of a difference. So to go back to this, what this says is that if you're interested in actually making a difference, you want to work on things that are as close to reality as you can, and you want to work on things that are as certain as you can. But the problem is if you're in a university, you typically want to work on things that are longer term and uncertain. And so how do you resolve those two? And the answer is nobody knows right now. You'll figure it out, those of you who are young. One way of doing this that is gaining popularity in the U.S. is to focus on what are called inevitabilities. The idea here is that if you can deal with things that have the characteristic, choose problems that have the characteristic that they are inevitable. You know that there's going to be a water problem in major cities. I mean, there's no question about that. So technology that generates water will be used somewhere, stands a high chance. So you reduce technical risk. You don't reduce the time to market, but you reduce technical risk. And what are some of these inevitabilities? One of them is population growth and maybe collapse and the development of what are called megacities. Mumbai now, greater Mumbai is about 50 million people in a single city. We don't actually have any idea how to handle that number of people. Age. Here is one of these things which you're probably familiar with, the so-called population pyramid. And each one of these bars here represents the fraction of the population. This is in the U.S. About 5% of the population of men are between 55 and 59. And if you look at these for different countries, you see interesting things. And I'll point out just two of them. One of them is if you look at Afghanistan, there are very large numbers of young people. This part of the population pyramid is growing. And the one thing you know for sure in the world is lots of unemployed young males means trouble. So Afghanistan is in for a long period of trouble. This is Japan, and what you see in Japan is continuing population decline, and Japan is now facing a population decline of such magnitude that if it doesn't change its immigration strategy, it will probably go out of business. It'll cease to have a self-sustaining population in about 20 or 30 years. So these are very interesting problems to consider when one is thinking about technologies. Information technology, a lot of this is electrochemical or nanotechnological. And I want to just show you one because it is so interesting and so unfamiliar to chemists. One of the most important inevitabilities is going to be that, you see it in Europe, you see it in the United States, there aren't enough jobs for the people. And that's on the one hand. The other hand is that jobs are being created in China and India much more rapidly than they're being created in Europe and the United States. How are we competing with China? How will we compete with China and India for jobs? And one of the major ways is that we will move to robotics. Now, robotics have many interesting features, but one of the unfortunate features of robotics is that they it moves jobs from people to machines. And I want to show you a video if you haven't seen it. Here's my cursor. This is a thing called Big Dog, and it's made as a pack animal, basically, for the military. But what I'm going to show you is how it maintains its balance without a brain. It has no brain. It's just a collection of accelerometers. So, and the point of that is that it passes, in some sense, what I would call the Turing test for motion. That is, if I look at that, I actually can't tell that it's not alive. You know, if you look at the joints, they're not hinged correctly. But you know, this thing, it's doing better than I would do in the snow with my eyes shut and no brain. And if you watch it in just a second, here it is going uphill. And it'll go down, and there's just one little section I want to show here. In a moment, it'll slip there. Now, that looks just like, to me, what an animal would do. What this says is that robotics has progressed to the point where it is basically, in terms of motion, it's as good as many kinds of animals are. And it's the rate at which this progresses is going to be enormously rapid. So it is an inevitability driven by labor costs and by the hazards of military operations these days. And so how do you fit power and other things into that kind of question? All right, just one or two final technical things. We have now an economy which is based on this kind of picture. You start from petroleum, most of it goes to fuel, a little bit goes to petrochemicals, which ends up in commodities and so on and so forth. You're familiar with this kind of thing. If we switch to nuclear or extensive use of solar or solar thermal, what we will have is heat, probably hydrogen, electricity, and opportunities to start using electrocatalysis and things of that sort on a very large scale. And this problem is one which is very strongly electrochemical and catalytic in its components. Right now we have an economy which is based on the idea that you start from hydrocarbons and you use oxygen to make oxidized intermediates. Can we start from CO2 and make the same materials by electroreduction? And it's fascinating to me that after many years of trying, as far as I can see, there are no really efficient methods of forming carbon-carbon bonds by reduction of CO2. You can make oxalate, but it doesn't get you very far and it doesn't work very well. So here is a fabulous problem for those of you who are interested in electrosynthesis. And here's another very interesting problem. If you look at hydrogen generation by electrochemistry, as I said, by electrolysis, it's quite inefficient right now. But there have been a number of cycles developed which generate hydrogen by using heat and can be coupled into solar thermal. This is just one. Copper, HCl at 400 degrees gives hydrogen and cuprous chloride. Cuprous chloride disproportionates rapidly to cupric and copper. The cupric chloride can be hydrolyzed and at 550 degrees disproportionates to give oxygen and HCl and cuprous chloride. This goes back to here, that goes to here, and the overall efficiency with which you generate hydrogen is supposedly about 50% as opposed to thermodynamic efficiency based on heat, as opposed to about 50% based on energy and electrochemical cycles. Whether these are ever used or not is an open question, but if you look at this as a source of materials that can be coupled into electrochemistry or materials like copper and cuprous chloride as an oxidizing agent, activating agent for olefins, cupric chloride is an oxidant, it's a very rich field of chemistry for doing things with. Now I'm going to finish off just by one tiny bit from our own research. 80% of energy is derived from carbon fuels by combustion, and that means by burning something. And you know, flames have been around forever, so we must know everything about flames. And it turns out that we actually know amazingly little about flames after all this time. And so we started on a project some period of time ago to look at this with the hypothesis that there's a different way of thinking about a flame. As a chemist, I tend to think of a flame as a chemically driven source of heat. But the temperature, even in a candle flame like this, in this region, is somewhere in the order of 1,500 degrees. And it's also a temperature that's high enough to make a plasma. So a flame is also a chemically driven plasma. And it turns out that on that basis, you can do all kinds of interesting things with flames. So for example, you put a flame in an electrostatic field and it deflects. You can make the flame burn horizontally if you want. And here's an example. These are just showing this horizontal thing here is partially something called an ionic wind, and is partially the plasma in the flame responding to electrostatic fields that are here. Now I show you this not because I think it's necessarily something that's immediately useful, but rather to make the point that in many of these areas that generate energy by time-honored methods like combustion, if you go back into them with current science and ask, what more can you learn? The answer is a lot. There's just, to take flames as an example, we just don't understand them. And that's very attractive as a basic way of beginning to think about new sources of technology. Incidentally, I do think that the idea of doing electrochemistry in flames, which is coming up increasingly, is a very interesting idea. So let me finish with this slide. If I go through all of this and look at it from the perspective of what kinds of things I would be doing if I were starting my career, what kinds of problems would I be thinking about, you still have to come up with a good idea. It would be some of these. One is catalysis, because everywhere you look in the energy production and consumption, catalysis is critically important, and heterogeneous catalysis remains almost completely empirical. So all the science remains to be done there. Materials with extreme properties, that is very low corrosion or friction, high temperature stability for high temperature fuel cells, high durability, very low weight, whatever. The invention of new materials for this world is extremely attractive, and if you can come up with a new material, it will be very, very useful. Mobile electrons and matter will pass this by for the moment because it doesn't really apply to what we've been talking about. Separation seems mundane, but as I mentioned, separating methane from CO2 and nitrogen changes the world, if you can find a way of doing it. Separating pure potable water from salt water changes the world, if you can find a better way of doing it. Very, very important. Biomimetic and biological materials. Think about what the leaf does in photosynthesis and ask how you can do some of the same kind of thing. Nanotechnology as an enabling possibility for these kinds of things. And then what I call impossible materials. If I say to you, can I make a liquid transparent ferromagnet? I don't know anything in physics that says I can't, but I have absolutely no idea how to do it. And if I could do it, it would completely change the world. So what do you know about materials that you just assume to be true? And then is it necessarily the case that it is true? Ask that and ask if you can make materials that are truly impossible. So it's a wonderful area, and it's going to have the characteristic, this is energy broadly, it's going to have the characteristic that there will be money there, so that it will be possible for universities to do research. And one of the key issues is going to be, as we do research in it, are we actually trying to solve a problem, or are we just trying to relabel what we've done already? If we try to solve the problem, it's probably 100 years of very good support. If we just try to relabel what we're doing, what will happen is what's happened in a number of other areas, which is it'll go on for about 15 years and then. So, not a good idea. So I hope that what this has done is to give you a little bit of a sense for at least how the U.S. views broadly the perspectives in this area of energy, nanochemistry, electrochemistry, and material science, and provide some context for the very interesting and more more detailed talks that will go on during the next couple of days. I thank you very much.
Thank you very much for this mind-opening or inspiring lecture, and you showed us that there is still a lot of things to do, especially for electrochemists. So we agreed just before his lecture, because he has to leave us tonight, and there will be no more opportunity for discussion, that we could accept, even though that it's a plenary lecture, that people ask 1 or 2 questions. Are there questions in the audience? Gunther?
I have one question. When you set up the scene for this energy supply demand setting, it seemed to me that one of the constants you assume is the pricing, so that the pricing will stay the same as it is now. But pricing is essentially something society decides in one or the other way. There could be a radical change in pricing which makes a big difference, and that's completely decoupled